Okay, we're going to talk about energy and work. We're going to leave out simple machines. That's not something we're going to cover for now. We're going to talk about energy and work though. So, first of all, work. The formula for work is force times distance. This is on your formula sheet. Okay, the tricky part about work though is you need to understand that the work that's done is only the force that's in the direction of the displacement. So what that means is if you're pushing on something at an angle, say you're pushing on a box at a 45-degree angle, and you have a force of 5 newtons, then the work formula, say you move this thing 10 meters, the work that's done is not the 5 newtons, it's not 5 times 10. The work done is only the force that's in the direction of motion, which would be this component of that force, which would be like, we'll call that the x component, which since this is 45, 45, 90, this is x squared root of 2. And you can divide both sides by the square root of 2 to find each of these, if you remember your special right triangles from geometry class. Or you could use SOHCAHTOA. Either way, you're going to get 5 divided by the square root of 2 for this component that's acting along the vector of displacement. And that's what you're going to have to use here. Okay? I realize that gives you an irrational number, which turns into about 35.4. And then the units on that are joules. Quick. And so the units, let me show you that real quick. But right here, the units are kilogram meters squared per second squared, which we're going to call a joule. Okay? And what was just pointed out, same thing with work, it's force times distance, so a newton times a meter is also a joule. And you'll see that they're the same if you go to it and plug in a newton. So a newton is really a kilogram meters per second squared, since F equals ma, right? We know that force is in newtons. So a newton is really a kilogram meter per second squared times that meter right here, and that's how you get the kilogram meter squared per second squared, which is a joule. So either way you want to look at it, you get a joule, which is defined as kilogram times meter squared per second squared. Okay, we've talked about energy already. I've shown you that SciShow video, but the definition is the ability of an object to produce a change in itself or the world around it. We're going to have several different types of energy. Let's start off with kinetic energy, which is the most basic kind that you're familiar with. If an object's moving and it has some mass, then you know when it hits something, you see it produce a change in something else, right? And so it definitely has energy. And that formula that relates the quantity, the magnitude of that energy, is 1/2 times the mass times the speed that mass is traveling squared. Okay. Once again, you're going to notice the units are joules again, a kilogram meter squared per second squared. And the reason that is because of this all-important theorem right here, the work energy theorem, which basically says that work and energy are the same thing. Okay. Work is defined as the change in kinetic energy according to the work energy theorem. So work and energy are the same. So we can say that force times distance is equal to the change in kinetic energy. So the final kinetic energy minus the initial kinetic energy. So we can even write this if we substitute in the kinetic energy formula. But this is an important theorem. Basically now we know that work and energy are two and the same. We'll look at an example of that right now. Okay, so we've got a 105-gram hockey puck that's sliding across the ice. We know that a player exerts a constant 4.5 newtons of force over a distance of 0.15 meters. How much work does the player do on the puck, and what is the change in the puck's energy? This problem's pretty easy. We know work equals force times distance. Since we're applying the force in the same direction of distance, we can just do 4.5 newtons times the distance of 0.15, and that gives us 0.675 joules. We also know that work is equal to the change in kinetic energy. So it says how much, what is the change in the puck's energy? Well, we know the change in the puck's energy is exactly what work was, which is 0.675 joules. So that's the answer to both of those questions. Let's try another one. Let's say a sailor pulls a boat at a distance of 30 meters along the dock using a rope that makes a 25-degree angle with a horizontal. How much work does the sailor do on the boat if he exerts a force of 255 newtons on the rope? Okay, this problem gets a little more difficult because now instead of giving a force that's in the direction of motion, we're pulling off at a 25-degree angle on this boat. So that's the boat. And we're pulling up at a 25-degree angle with 255 newtons of force. So we're going to use the same equation, but this time the force that we use has to be this force here. I'll draw with this orange vector. I'll call that F of x. That's the force we need to use because that's the force that's pulling this boat the 30 meters in that direction. So the force that we use has to be in the same direction as the displacement. So we're going to use cosine of 25 equals adjacent, which would be F of x, over hypotenuse, multiply both sides by 255, and that's what I use for my force right there. That's the force in the direction of motion. So work would be equal to 255 times cosine of 25, that's the force, times the distance of 30 meters. And if you do that, you should get about 6,933.3, and that's joules for work. Next equation I'm going to give you is power equation, which is on your formula sheet. Power is the amount of work you do in some time interval. So power is basically, it's a joule per second, which we're going to call a watt. So watt is a joule per second. It's how much work you do in a certain amount of time. Okay? Yeah, so here's the power equation. Don't be confused between work and watts there. This is work for a problem. This is watts, the unit on power. Okay, so let's try an example problem with that then. I am going to give you a net force of 2,800 newtons that accelerates an object, a vehicle, for 8 seconds. The vehicle travels 80 meters during this time. What power output does this represent? All right, so the power, we're going to use power equals the work that you do divided by the time that you do it for, right? And they give us enough information for this because we know work is force times distance, so it's really force times distance over the time. The force is 2,800 newtons times the distance of 80 meters divided by the time of 8 seconds. 8 seconds. So that will give you the answer of 28,000 watts. All right, next we need to talk about the conservation of energy. So I've already given you this formula for kinetic energy. I'm going to give you a new formula for gravitational potential energy. So if we do some work on an object to move the object up to some height, then that object has what's called gravitational potential energy. It's got the potential to accelerate downward and create a change in the environment around it, right? So it has energy. And the form of energy that we'll say it has is gravitational potential energy, which is equal to the mass times 9.8 times, well, I should say times the acceleration due to gravity, which will change depending on what planet you're on and how far you are away from an object. And then times the height that you are away from a reference level. Okay? And we'll talk about all this, and it'll make more sense as we go over some example problems. So let's try one right away. Let's say that you lift a 7.3 kilogram bowling ball from a storage rack and hold it up to your shoulder. The storage rack is 0.610 meters above the floor, and your shoulder is 1.12 meters above the floor. Okay? So let's draw a picture of this real quick. The storage rack is, let's say here. How can I draw a good picture of this? So we're going to take this bowling ball off this table. It's currently at 0.610 meters on the table, and we're just going to lift it up to our shoulder height, which is 1.12 meters above the floor. Okay? And they told us to use the floor as our reference level, so we're going to use that as our zero gravitational potential energy. Now, obviously, you have to look at this as something could keep falling as long as it can fall. So if there was a hole dug here, the bowling ball could fall further, in which case it still has gravitational potential energy depending on where you start your zero mark. Does that make sense? Does that? So for part A, we know that gravitational potential energy is equal to mgh. All right, so relative to the floor, when it's at your shoulder, we're going to use the mass of the bowling ball, which is 7.3 kilograms, times gravity, which is 9.8, times the height of our shoulder, which is 1.12. And that gives us 80.1, and we're going to use joules for that, right, because that's energy. All right. Now, part B says, when the bowling ball is at your shoulder, what is the gravitational potential energy relative to the storage rack? Relative to the storage rack now, we're only looking at this as our height. 1.12 minus the 0.610, which gives us 0.51. So we're going to use the same formula. Potential energy is equal to mgh, but this time 7.3 and 9.8 stay the same. and the distance or the height changes because we're talking about just the height from your shoulder to the storage rack, which is 0.51 meters. And that gives you 36.5 joules. Okay? And then the last question says, how much work was done by gravity as you lifted the ball from the rack to the shoulder level? So work, well, I'll use force times distance for this. The force that we're putting on the ball to lift the ball would be mass times gravity. That's the force we're exerting to lift the ball, times the distance that we lift it for. And you're going to notice this is the same exact formula. So 7.3 times 9.8 times the distance we lifted from the table to our shoulder is 0.51, which gives us the 36.5 joules. So you can see that we've basically shown for this one case, and it's true for all cases, that the work is equal to the change in energy as we lift this ball. So if you want to know how much work we did in joules, all we have to say is how much energy, what was the change in energy from this point, from the table to your shoulder.